Welcome back, everyone. Ready for another deep dive?
Always ready to explore the universe's mysteries.
And today, we're tackling a big one, right? I mean, a really big one.
That's an understatement. We're talking about dark matter, the stuff that makes up, like, what, 85% of the universe's mass?
Crazy, right?
Yeah.
And the thing is, for the longest time, scientists were pretty sure they knew what this mysterious dark matter was.
Yeah, WIMPs were the hot topic for years, these weakly interacting massive particles.
WIMPs, okay. I'm guessing those turned out to be a bit of a dead end.
Well, not a total dead end, more like a detour. But that's science, right? It's all about following the evidence wherever it leads, even if it takes you down some unexpected paths.
And in this case, that path leads us to axions.
All right.
Yeah, axions, the new kids on the block in the dark matter search.
Okay, I'm all ears. But before we dive into all that, let's take a step back for a sec. For those who might be new to this whole dark matter thing, what exactly are we talking about here?
All right, so imagine you're looking up at the night sky, all those stars and galaxies. Beautiful, right? Absolutely stunning.
But here's the thing. All that stuff we can see, all the stars, planets, gas clouds, even black holes, it only accounts for a tiny fraction of the total mass of the universe.
Tiny. How tiny are we talking?
Like less than 20%. The rest, the vast majority, is this invisible stuff we call dark matter.
Invisible, so how do we even know it's there?
Because of its gravity. We can see its gravitational pull on the stuff we can see. Like, galaxies are spinning way faster than they should be based on the visible matter alone. And the only way that makes sense is if there's a ton of invisible matter, this dark matter, holding everything together.
So it's like the cosmic glue, keeping the universe from flying apart.
Exactly. It's the scaffolding, the framework that everything else is built upon.
Okay, that makes sense. So back to the invisible suspects, right? We were talking about WIMPs.
Right. WIMPs, or weakly interacting massive particles, were the prime suspects for decades. The thinking was they were these hypothetical particles that interacted very weakly with normal matter, kind of like ghosts passing through walls.
So hard to detect, but potentially everywhere.
Precisely. And they fit nicely with some theoretical predictions.
Like what made scientists think WIMPs were the answer?
Well, there's this thing called the WIMP miracle. Basically, the theory predicted that the amount of WIMPs created in the Big Bang would be almost exactly the amount we observe as dark matter today. It was like, wow, this must be it. It was so elegant, it had to be true.
But it wasn't, right? So what happened? Why did the WIMP miracle fade away?
Well, scientists built these incredibly sensitive detectors, buried deep underground to shield them from cosmic rays and other interference, hoping to catch a WIMP interaction. And then there was the Large Hadron Collider. Smash particles together at crazy high energies, maybe create some WIMPs in the process.
Wow.
Nothing. Zilch. No WIMPs showed up. Years of searching, some of the most sophisticated experiments ever built, and nothing.
Wow, so it's back to the drawing board then.
Pretty much, and that brings us to axions.
Axions, tell me more. What are they?
Okay, so axions actually came about trying to solve a different problem altogether. They were first proposed in the 1970s to explain a quirk in the strong force, one of the fundamental forces of nature.
I'm with you. The strong force, right? It holds atomic nuclei together.
Exactly. But there was this weird thing. Quantum chromodynamics, the theory that describes the strong force, predicted that it should violate something called CP symmetry, basically a kind of mirror symmetry in the laws of physics. But experiments showed no such violation.
So the theory and the experiments didn't match up.
Exactly. It was a head-scratcher. And that's where axions came in. They were proposed as this extra ingredient that would restore the symmetry and make the theory fit the observations.
So axions were originally a fix for a theoretical problem. How do they end up becoming dark matter candidates?
Well, it turned out these axions, if they existed, would have some very interesting properties. They'd be extremely light, practically invisible, and interact very weakly with normal matter. Sound familiar?
Sure, sound a lot like dark matter, yeah.
Exactly. It was like, wait a minute. These things we invented to fix the strong force, they might actually be the dark matter we've been looking for. It was like a happy accident.
Two birds, one stone. Love it when that happens in science. But if axions are so elusive, how do we even go about looking for them? I mean, it's not like we can just point a telescope at the sky and say, hey, there's some dark matter.
True. It's tricky, but physicists are clever. One approach is to use these things called haloscope detectors. They're basically big, supercooled cavities filled with strong magnetic fields. The idea is if an axion passes through this magnetic field, it might convert into a photon, a tiny flash of light that we could detect.
So we're setting a trap, hoping an axion wanders in and reveals itself.
Exactly, like luring them out of hiding. So far, no luck, though. But then there are other cool ideas, like using pulsars.
Pulsars, remind me what those are again.
They're these incredibly dense, rapidly rotating neutron stars. Like, imagine the mass of the sun crammed into something the size of a city, and they spin like crazy, some of them hundreds of times per second. And these pulsars have insanely strong magnetic fields, and the thought is those magnetic fields might interact with axions in a way that produces detectable radio waves.
So pulsars could act like cosmic axion beacons. That's awesome.
It is, and the search is just heating up.
This is fascinating stuff, really.
Yeah.
But I have to ask, if axions are such a good fit for dark matter, why are some scientists still hesitant to jump on board?
Well, there's this whole debate about fine-tuning. Some axion models require a lot of tweaking of parameters to match observations. It's like, yeah, you can make it work, but it feels kind of contrived, you know?
Like forcing the pieces of a puzzle to fit even if they don't quite belong.
Exactly. And some physicists find that uneasy. They say, look, if we have to fine-tune things so much, maybe we're barking up the wrong tree. Maybe there's a more natural explanation out there.
So where does that leave us? Axions, yay or nay?
The jury's still out. But honestly, they're probably the most promising candidate we have right now. They address a problem with the strong force, they naturally explain the smooth distribution of dark matter, and we have some really clever ways to look for them.
Not bad for something originally invented to fix a different problem altogether, huh?
I know, right? It just shows you how interconnected everything is in physics.
So what's the takeaway message for our listeners today? What should they be pondering as they go about their day, encountering this invisible dark matter all around them?
I'd say keep in mind that the universe is still full of mysteries. We've been studying the cosmos for centuries, and yet we still don't know what most of it is made of.
And the answer might be stranger than we can imagine.
Exactly, and that's what makes it so exciting. The quest to understand dark matter is a reminder that we're still just scratching the surface of what's out there.
And who knows what incredible discoveries await us as we continue to explore. Thanks for joining us on this deep dive into the world of dark matter. Stay curious, everyone, and we'll catch you next time.
See you then.